Hello, everybody, and welcome to our senior project we've been working on this semester and it's called YS-2, Generative AI and Cybersecurity for the fall semester 2024 with our professor, Sharon Perry. My name is Seth Canada, and I'm here with,
Shreya Katare.
and I will go ahead and go over the table of contents of our presentation. Basically, first of all, we want to say what is generative AI and what are its effects on cybersecurity and how does our neural network work, basically. And then we want to go over our 5 different modules. And our first module is anomaly detection. What is it and what is its impact on generative AI? And we want to show a demonstration of it, of our model working with certain algorithms with anomaly detection. Then we want to go over IDS. What is it? Its impact. Malware analysis. What is it? What is its impact? And then we have deepfake phishing. What is it? What is its impact? But we also have a demonstration with that with its algorithms and how our model works with that. And then we have more polymorphic malware. What is it and its impacts on it as well.
So, generative AI is a type of artificial intelligence that is based on existing data and known knowledge to create new data. And this has either a positive or a negative impact on cybersecurity. Like there are some ways, like anomaly detection, intrusion detection systems, and malware analysis that may improve security. If we're thinking of the ways that may threaten cybersecurity, it can be with deepfake phishing and polymorphic malware. So going into our first case study that we analyzed is anomaly detection. And this is a technique used in cybersecurity to identify unusual patterns or behaviors within a dataset that may indicate a security threat. With generative AI, it can be a very helpful way for network traffic, and it could identify potential threats in the anomalous patterns with the use of machine learning algorithms to analyze the traffic data in real time. So these algorithms are generative adversarial networks and variational autoencoders. GANs are used with a discriminator node and a generator node that is creating new data sets, and it is also discriminating between fake and real data. Vase are used with a latent space. It is compressing data into this space and then adding a variational component to it and then decoding that after. And GANs and Vase could be used as a hybrid algorithm, and that is what is shown in the image to the right.
So next up, what we're going to be doing is demonstrating our neural network and how it works with anomaly detection. And so I'm going to go ahead and show you. So here's our first demo that we created for our project. And basically what it does is that it just basically imports all the pre-processing modules that we need. And then it imports what I like to call a data loader file that we created. And it loads in our network traffic data, which is one of our data sets that we were using. And it basically splits it off into an X train and then an X val, basically our testing. And we have our basic object of VAE, and that's from our VAE.py that we created from scratch as well. We want to go through 50 epochs with a KL loss weight of about 0.001 with a learning rate of 0.0001. Very small learning rate, but it's able to not overfit or anything like that. And we have anomaly threshold of 0.3, basically. And it basically goes through each epoch and does forward propagation and does the reconstruction loss of the algorithm and basically calculates all the losses together and does backward propagation and then finally displays it, the total loss, the reconstruction loss, and the KL loss, and then finally goes through and does its predictions, is able to display its scores of anomaly Basically, everything on the left would be actual network traffic, and everything past the threshold, the red dotted line, would be everything that's considered an anomaly. And it also displays the overall graph for the model's performance, basically. And so here we go through each epoch, and as you can see, total loss, VAE loss, its loss decreases over time, which with each epoch. And as you can see, it does the same thing with V reconstruction loss. KL loss, you actually want it to improve, but it also to be stagnant and very low. So we want to decrease loss as much as we can. And as you can see here, it was doing that. As you can see with our distribution of anomaly scores with threshold, here's our red dotted line. It falls right on everything here was where exactly we want it to be. So everything on the right, basically 6,299 of the out of the 125,000 different network traffic data that we had, 6,299 of them were anomalies, as you can see by the threshold. And by the training, the loss became lower and lower as time went along. And as you can see, the KL loss remained very low and stagnant.
So the next case study we'll go over is intrusion detection systems, and this is a type of security mechanism for network traffic by detecting harmful activities. And with generative AI, it can again be an optimal solution for both generating realistic network traffic as well as anomaly detection. It is very powerful for advancing the capabilities of existing IDS systems and allowing the systems to handle more complex attacks and improve detection accuracy. The algorithms that work for IDS are signature-based IDS, which is shown to the image to the right. And what this does is looking through a known list of signatures attacks and understands whether the anomalies are something that is known. Anomaly-based IDS is looking for out-of-the-ordinary triggers to understand whether something is an anomaly. The next module is malware analysis, and this is a type of system processing for determining the functionality, origin, and potential impact of a given malware sample and extracting as much information from it. With generative AI, it could again impact it positively by transforming how malware is detected, analyzed, and mitigated. Its ability to generate new data, model complex patterns, and simulate some sophisticated malware threats enables the security systems to be more proactive and adaptive in combating malware. The algorithms that could work for malware analysis is deep reinforcement learning and long short-term memory, and both of these are used with a type of long-term memory inside of it, and this is very helpful with the generative AI component. Deep reinforcement learning is shown to the image to the top right, and long short-term memory is shown to the bottom right. LSTM is actually a type of recurrent neural network, which is using a past memory, but this is short-term, so LSTMs are much better for the generative AI component. So the next two modules we'll go over are the negative impacts on generative AI, and the first one is deepfake phishing, and this is a type of security attack that is aimed towards users to scam them into revealing or providing their private data for malicious purposes. With generative AI, again, this could further threaten a system through its sophisticated algorithms, and it would be much more difficult to mitigate the attacks and differentiate between a scam and reality. The algorithms that work with this are GANs again, and the way it works is that it would generate new data and then use the discriminator node as basically a proxy to understand what is fake and real, and this would be much harder to mitigate. But you could use something like a convolutional neural network, which is used with its layers, like the convolution layer, pooling layer, and the fully connected layer to extract as much information from a data set and understand what is fake and real data. And there is also the vase that could be used to do the deepfake phishing. And what it does is compressing the data into latent space. And during the part where it adds a variational component, it is able to make it much harder to mitigate since it is very similar to what real data is looking like. But you could use something like natural language processing, which is differentiating between fake artificial intelligence data content and what is human-like content if we were using a data set with email phishing.
Next up, what we want to do is that we want to show demonstrating our deepfake phishing algorithm using GAN and how our model works with that. So let me go ahead and show that as well. So as you can see with our next one is that we basically just kind of followed the same thing where we imported a bunch of different pre-processing, and then we imported a bunch of metrics, and then we wanted to import our data loaders, and we want to, here we loaded in our phishing emails and our labels with that one using the data loader class that we created. And basically what we did was is that we condensed down all those labels to about like 10,000 here, and then we basically used our unified network and just made the object with that one, and then we used GAN and then used our actual file, our actual object GAN, and we basically made a generator and discriminator, and we wanted about 10 samples of it with a noise size about 100 and with a threshold about 0.5. And then within here, we decided to use the GAN to generate those deepfake phishing emails, basically. And then we had the discriminator start predicting whether it could detect the synthetic or the real emails. And basically, we converted it into binary predictions, basically a 0 or a 1. And we basically just made some labels ourselves, and basically we printed out all of the basic predictions that I made, and then we also went down here and basically had it do different kind of metrics if it could, and then did uh, basically a real mean and an STD of the real synthetic, sorry, the real email, and then we had generated mean and STD, and it showed us the different ways that they compare to each other, basically. So as you can see here, we had its shapes and everything, and we printed all that out. But then we had an accuracy displayed here, and that's what we wanted, basically. So it was able to predict and generate and everything. So its real mean data here, as I was how it relates to each other, is that it's about as close to 0 as it could, and then its generated data was as close as it could to 0, but it wasn't exactly 0, which means that there were discrepancies within it. So it was actually doing what it was supposed to be. It's not exactly the same thing, which is good. And its real data STD should be 1 or close to 1 as it could. And generated data, also STD, was about as close to 1 as it could as well. And as you can see, it wasn't the same thing, as you can see. And that's the best way to put it in terms of it actually recognizing that the generated and the real are actually different.
So the last module we'll go over is polymorphic malware, and this is a type of cybersecurity attack associated with malware where it can mutate itself and make it much harder to mitigate with regular security systems. With generative AI, it can be used to automatically generate new variations of the malware with different code signatures, encryption methods, or file structures while retaining the malware's malicious behavior. So the algorithms that could work for this module is again GANs and VAs, and they could both be used in a way with a mutation type of process like it is shown in the image to the right, but they could both be mitigated with something like a anomaly-based IDS or some some solution that uses out of the ordinary triggers to alarm a user when there is a mutation or a polymorphic mutation that is occurring in a system.
Lastly, we want to conclude by saying thank you for listening to our project and being with us the whole way through this demonstration. Basically, our research sought to examine how a generative AI can both enhance and pose risks to the cybersecurity of a system. The research project demonstrated that anomaly detection, IDS, and malware analysis are tasks that a neural network may improve, while polymorphic malware and deepfake phishing can be generated from a neural network as well. And these results indicated that while the neural network effectively boosts cybersecurity capabilities, further fine-tuning is required for optimal performance, emphasizing the dual role of generative AI as simultaneously a valuable asset and potential challenge in the field of cybersecurity. Thank you.